So let's start this session. The topic for this session is differentiation. It's a very interesting and very important topic. And to understand differentiation, you must have a good understanding of slope and graph, which you have done in previous sessions. So before you begin, make sure that your understanding of slope and graph is good. And as I said, it's extremely important topic and interesting as well. Right, so let's understand this topic of differentiation with the help of some physics examples. See, so this is a concept. See what we see here. We talked about graph in the previous case. So what does this graph indicate here? This is a position time graph, and if position is measured along x-axis, we call it xt graph. So xt graph is given, and unlike previous session, this is not a straight line. So what did the straight line indicate? Slope of the xt graph indicated velocity, and velocity was constant. It was a straight line. No, it is not a straight line, it's a curve. This basically indicates the velocity is not constant. Okay, so let's proceed further. And most graphs, if they're drawn to certain basic principle based on certain mathematical expression, something like this. So this graph is drawn based on this mathematical expression, x is equal to t square. So t is plotted on the x-axis and x is on the y-axis. So for every value of quantity on the x-axis, we can find the quantity on the y-axis. So time t is equal to 0, x will be 0. For time t is equal to, say, something like 0.3 second, it will be equal to 0.3 square. 0.3 square will be 0.09. So 0.3 it will be 0.09. And likewise, so we can plot this graph. This plot is position time graph for position time given by relationship x is equal to t square. Okay, so any equation. So whenever we have two variables related in terms of mathematical expression, a graph can be plotted. A 2D graph can be plotted. Now, suppose we pose a question to ourselves. What is the average velocity between time t1 is equal to 0.5 second and t2 is equal to 1.1 second? And whenever we talk of average velocity is always over a time interval. So whenever we talk about time interval, there's a beginning instance of time, there's an end instance of time. A beginning instance, I can say initial time and final time, or t1 and t2. Excuse me. So what is the average velocity? So using either this equation or the graph, can we find the average velocity? Okay. So if I'm going to use the graph, let me mark the points on the graph corresponding to these two instances of time. So corresponding to T1 here, this is point T1 here. This is the point on the graph corresponding to T1, and similar to T2, corresponding to T2. This is the point on the graph here. So once we identify the point graph, we can find the corresponding value which is displayed on the y-axis. Okay, so like this. So what does this particular point indicate? From here, we find the y coordinate corresponding to this point. And since we are talking about T1, y coordinate, let me say T1 is equal to 0.5 second, and on y-axis we have x coordinate. I can use something like this. I can write like this also. And many times we use this notation to for the sake of brevity, but let's make it more short. So what does this indicate? Position of the particle at time t is equal to 0.5 second. This is the value here. And similar way, what is this point here? This also, what is there plotted in y-axis is x coordinate, and this is a time 1.1. And we can read this value also. And see these values. See, graph is this is not a, we don't have smaller divisions here. It's difficult to read. But what we understand here, what is this particular point? It is above 0.2. This is the 0.25. And this point is little above 1.2. So it is, though it might be difficult to read the graph, since the equation is given, we can find this y coordinate for this x value being 0.5 or value on x-axis being 0.5 is 0.5 square. So this value will be 0.5 square and this will be 1.1 square based on this equation. So we know this position. So how do we interpret this one? It means at time t is equal to 0.5 second, the particle was at a position of 0.25 meter on x-axis. At time t is equal to 1.1 second, it is at a position of 1.21 meter. Now we need to find the velocity. To find velocity, first average velocity, first we can find displacement. What is displacement? Displacement is equal to final position minus initial position. It has moved from 0.25 to 1.25. So what is the displacement? It is moving towards right direction. Displacement is positive, and the difference of the two will give displacement. Final position minus initial position. That's a 0.96 meter. So it has moved 0.96 meter during this time interval. So we can find average velocity, and that's a definition of average velocity during the time interval, displacement by time. So if you put those values here, it comes to 1.6 meter per second. Okay. So during this interval, this is average velocity, and this is something from from the graph also we can find the two values, two positions. We can find the displacement by time. So we can find average velocity. Let's try and understand what does this average velocity mean. Does it mean the particle has been moving with the speed of 1.6 meter per second during this time interval of 0.5 to 1.1 second? Actually, no. See, had it been moving the constant velocity, the graph would have been a straight line. The fact it is not a straight line, it doesn't mean that average velocity is 1.6, but it doesn't mean that all through the duration it was moving with that velocity. So it means if average is 1.6 for certain duration during the time interval, its velocity was less than 1.6, and some interval it must have been greater than 1.6. Both ways, then only average has come to 1.6. Okay, so that point also is clear. As the xt graph is not a straight line, velocity is not constant, it is varying. So average velocity during time interval, velocity is varying, but the average velocity is 1.6. So this is what we understood. So this is and we continue further. So we'll continue with the same graph in next slide also. We'll explore further what we had done from the previous slide. Yeah, during these two instances of time, average velocity is 1.6 meter per second. What if we draw a secant? What does secant mean? Secant is a line which intersects a curve at 2 points. That's a secant to a curve. And let's draw a secant in such a way that it passes through these 2 points. So can you visualize, or can we draw a secant here? Okay, let me draw a secant here. It's a secant here. This is secant to the curve, intersecting at the 2 points at time t1 is equal to 0.5 second and t2 is equal to 1.1 second. Now, yes, so this is straight line. So any straight line will have a constant slope. So can we calculate the slope of this line here? And the question is, and then we have to think of what does the slope indicate? Let's do both. First, let's calculate slope and also think what does slope indicate? How do you find slope of the straight line? We pick up any 2 points, we pick up. And since 2 points are already marked on the straight line, let's pick up these 2 points here. This point and this point, they lie in the straight line. They lie on the curve as well. So let's choose 2 points which are on the line where it intersects the curve. So we calculate the slope of the line. Again, slope of the line can be calculated as a delta of quantity on the y-axis divided by delta of quantity on the x-axis. So this will give you delta t, and this will give you change in quantity displayed on the y-axis, which is delta x. If we calculate again, this also, it exactly same expression we had on the previous sheet. So what is the slope of the secant? Slope of the secant is equal to average velocity exactly at what 2 instances? At 2 instances where it intersects the curve. So that's an important inference we can draw here. Slope of secant to xt curve is equal to average velocity between 2 instances where it intersects the curve. Average velocity is always between 2 instances. Which 2 instances? Where it intersects the curve at 2 points. So that's another way to interpret the secant here. So secant cuts at 2 points. Slope of the secant for xt curve gives you average velocity, right? So far we have talked about average velocity. There's also a term called instantaneous velocity, and note the difference between the two. When we talk about average velocity, we always mention a time interval. There's a beginning instance of time, there's an end instance of time. When we talk about instantaneous velocity, we are talking about only one instance of time. What is the velocity at the instant the time is equal to 0.7 seconds? So exactly, so not during the 2 point, at this point. So at this particular instance of time, what is the instantaneous velocity? So when we talk about instance velocity, we are not talking about 2 instances of time. We are talking one single instance of time. And we show it later that the velocity at this instance is equal to slope of the tangent drawn at 0.7 seconds. And how to find the slope? Because finding slope is not easy. We have to draw a curve, we have to draw a tangent, and we have to draw it properly and then measure the slope. How to find the slope of a tangent is a part of understanding differentiation. What does differentiation do? It makes the process of finding the slope of tangent easy. And slope of tangent, you need, if it is xt curve, slope of the tangent has a meaning. In xt curve, it indicates instantaneous velocity at the point of tangency. That's what you'll do. So if you have to draw a tangent, tangent would have looked something like this. The red color is the tangent at points corresponding to t is equal to 0.7 second. And you notice, so what is the blue line here? Blue line is a secant. Slope of the secant gives you average velocity at 2 points of intersection. Tangency has only one point of intersection, or we can call it point of contact. It has only one point of intersection, that's the tangent. Or point of, and slope of tangent gives you velocity at the point of tangency. These are two important points we need to understand in case of position time graph. Okay. Let's move further. Okay. So question is how to find slope is important thing we need to work on now. And that's what we are going to do. So let's how to find tangent. Okay. So where to find tangent, what we need to do, see, when we need to find, sorry, just let me do one more thing. See, when we talked about average velocity between 0.5 second to 1.1 second, that depends on what kind of motion is taking place between these two instances of time. Now, this is what is important, how it is moving between two instances. It doesn't matter what is happening before and after. Similar way, when I'm talking about instantaneous velocity at 0.7 second, actually I'm concerned about motion in and around 0.7 second. We are not concerned about the motion during other instances of time. So to find or to understand instantaneous velocity better, what we are going to do, we are going to concentrate only on that part of the motion which is around 0.7 seconds. So what we'll do now, we'll focus our attention only to a very small part of the curve around 0.7 seconds. Okay, so let's focus on our attention on a small segment of between 0.7 to, and a small, how do we define a small? So let's take, just for sake of our illustration, we take extending from 0.7 to 0.71. The small segment, and moment we make this segment small here, you notice one thing, you notice it start looking like a straight line segment. And that's what we'll find here. Any small segment of a curve can be approximated as a straight line. Okay, and we see kind of intuitive proof also that why it is a straight line. The straight line, what is the property of straight line? Straight line property is any 2 point you choose. If the slope comes same, it is a straight line. So let's see that part also. Which part are we looking at? We are looking at a very small segment, and for illustration, we are taking the segment from 0.7 to 0.7. So let's continue from here. So this is the part we are concentrating on. Since these are two ends, 0.7 and 0.71. So let's, for the sake of discussion, continue similar thing what you have done before. What is the average velocity at 0.7 and 0.71 second? If you have to find average velocity, and we know what is the curve? Curve is x position is equal to t square. So again, similarly, average velocity are okay. We can find where the particle was at 0.7 second. I can find position at 0.71 second, and then I can find displacement and average velocity. Similar what you have done before. So when we to find average velocity, and average velocity can be written as this position at 0.71 minus position at 0.7, difference gives displacement, and this is t2 minus t1 time interval. And when we calculate, it comes to 1.41 meter per second. And this average velocity is also equal to slope of the secant passing through these 2 points. That's another way to interpret. That's what you have done. Average velocity is equal to slope of the secant passing through those 2 points on the curve. Let's proceed further. So we have taken this time interval to be 0.01 second. Now step for, still we are looking at this part only, but now we have selected two other points. Which are the two other points we have selected? 0.7 second and 0.705. So we have made the time interval even half of this. So even this also a midpoint, and it is starting. Can we calculate average velocity similar way? Again, similar way. I can find out something like this. X 0.705 and x at 0.7. Difference will give displacement by time interval. Time interval is 0.005. Again, I calculate what is surprising, and this important point to understand here. This comes to mathematically, if you calculate, it was 1.41, this is 1.4. They are almost equal. And that's important point. And what inference can we draw from here? The fact that it has come equal, it means if we draw secant joining two endpoints or midpoint and the beginning point, slope comes same. Let's first of all, this is so small, it's difficult to understand what is happening. So assume that we is a magnified, slope is same. So it is something like this. If I magnify this point here, let's see something. This was the point corresponding to 0.7 second. And basically this part only, assume that we have just zoomed into this part here. Other end was at 0.71 second. We have chosen third point at midway between this. So that was 0.705 second. And what I find, if I call this point as A, and this point is B, and this point is C. Okay, so what is this one? Slope of line connecting A and B is equal to slope of line connecting A and C. The slope of line connecting A and B is equal to 1.41, and slope of the line connecting A and C is equal to 1.4, almost equal. So when this happens, when we have 3 points and line joining them have same slope, it implies those 3 points are on a straight line, or entire thing is a straight segment. So that's why, though there is a small error here, and this error here, this is 1.41 and 1.4. Had we taken even a smaller segment, even this error also, which is a small now, it becomes even smaller. And if we make the segment infinitely small, error becomes 0. That's another thing we understand here. And this understanding is important, and it helps in understanding many things later on in physics. If any curve also, if we take a very small part, it can be approximated as a straight segment. Slope is almost same. So it means this part is like a straight line. And part will, it is even closer to being a straight line if the segment is smaller. Okay, fine. So this is like a straight part. What else we understand from here? Okay, so we were interested in finding velocity at 0.7 second. Now, what you're saying now, if I am calculating average velocity in time interval very close to 0.7 second, okay, though it is average velocity, we can think it will be very close to instantaneous velocity. So instantaneous velocity, but if you make the time interval even smaller, see now here it was time interval was 0.01. Now we have made it 0.005. If we keep making time interval even smaller and smaller and smaller, we'll reach something called instantaneous velocity. And what would instantaneous velocity would be? It comes close to 1.4 meter per second. It looks like. But is it exactly that or not? That's what we'll see later on. We'll prove that point also. Right, so we get some idea how do you get average velocity, instantaneous velocity. So what you are saying now, what is this? How did you get this number? This number is a secant of a slope of 2 points very close to each other. What is saying? The secant joining 2 points negligible distance apart. If this distance becomes negligible, it is almost equal to a tangent. If the 2 points are negligible distance apart, it becomes like a 1 point. So secant, which is intersecting at 2 points 0 distance apart, is nothing but a tangent. So there's another way to understand a tangent. Tangent is it touches the curve only at 1 point. Tangent is almost equal to secant, which intersects at 2 points 0 distance apart. Negligible distance. We 0 it becomes tangent, we take negligible distance. And this concept is the basis for differentiation. Let's understand that part. Okay. So what is tangent? Tangent intersects at 0 distance apart. So we are equating with almost equal to secant, negligible distance apart. Thus we can use the concept here, right? So let's proceed further. So basically what we are saying, this is something, so this is what tangent is. Okay. So what is the concept of differentiation? Concept of differentiation is this: to find slope of a tangent, we find slope of a secant which is intersecting at 2 points 0 distance apart. So concept of differentiation, slope of tangent to a curve is by finding slope of a secant joining 2 points negligible distance apart. And let's apply this concept. So first we have understood why these slopes are equal, and why the secant, and can be when and under which condition can be secant is almost equal to tangent. Finding slope of secant is easy, finding so tangent is not easy. So that's why, since tangent has only 1 point, how do I find slope of a tangent? That's why we are approximating tangent to a secant. Because secant we can find the slope, tangent not so easy. And we are interested in finding slope of the tangent, because tangent of slope has important meaning. In case of xt curve, tangent is equal to instantaneous velocity at that particular point of tangency. So that's the idea behind this. Let's see in the subsequent slide, we'll understand how to apply this concept. Key point, slope of tangent is equal to slope of a secant, joining 2 points negligible distance apart. Let's apply that part here. So now again, so far we are talking about x is equal to t square. This also variable quantity, this also variable quantity. If we use normal mathematics convention, this is something on the y-axis quantity, this becomes x-axis quantity. So again, I can, if this is x, I can again revert back to y is equal to x square. Y is equal to x square is similar to this expression. Okay, so again, in place of position of particle, again I define variable y. In position of time, we define a variable x. So again, the shape of curve remains same. Only thing what will happen, the labels will change. This becomes x. Similarly, position also I replace with y. So same graph. Now I come back to moment I change the label, it becomes a typical mathematics graph. Why I'm reverting to mathematics? Now I'm going to more like understanding from mathematical angle, understanding derivation or concept behind differentiation. So slope of a tangent at x is equal to a slope of a secant joining x and another point very close to x. That's what we discussed. So how do you find slope? Let's do that. Let's apply this concept here. Okay. So what we have done here, if I want to find slope in terms of general point here, we're not into earlier we were talking about a specific point. Let's talk about a general point. So which point I want to find slope at? I want to find slope at x. So I have taken 2 points. One point is x, and another point very near to x. Okay. So these are 2 points I have taken. And if these 2 points are 0 distance apart, slope of the secant connecting these 2 points will become the slope of the tangent. That's the concept here. Let's apply it. So slope of a tangent. So what we do, we have taken 2 points here. One point is x. So what is the second point? Second point is a little more than that. The first point, second point is a little more. It is x plus delta x. So corresponding to this, there's a y coordinate also. What is y coordinate? This is y x, and this is y x plus delta x. So what is the slope of the line joining 2 points? What is the slope of the secant lining these 2 points on the curve? We can find easily. Delta y by delta x. Hence the slope will be equal to delta y by delta x. What is delta y? Y x plus delta x minus y x divided by x2 minus x1 quantity kind of thing. So what is y value? Y is equal to x square. Y is dependent on x, so y can be written in form of x. Then only you can find derivative. So what is this one? X plus this term will be equal to this point corresponds to x is equal to x plus delta x. Hence it will be square of x plus delta x. So y coordinate of this point will be x plus delta x whole square. Y coordinate of this point will be x square, and this expression, right? So can you simplify this expression? This is slope. This is slope of a secant of 2 points. Their horizontal distance is delta x. Now, what is concept of derivative, or what is concept of differentiation or tangent? It becomes a tangent when this delta x approaches 0. Then what happens is 2 points become almost 0 distance apart, infinitely small. So derivative, when we make this denominator of delta x infinitely small, how do we write it? We write as limit delta x is tending to 0. It is not 0, otherwise it becomes indeterminate. It becomes 1 point. It is tending to 0. Limit x tending to 0. This term is written as dy by dx. So delta y indicates a difference in y quantity. If the difference becomes very small, it is written as dy. So dy by dx, this expression is written by dy by dx. This is called derivative of y with respect to x. No. How is y changing for a small change in x? This is the term. So dy is a small change in y quantity for a small change in x quantity by dx. Can you find this expression here from here? So what I need to do is the same expression I have to use. Only thing this expression, I have to make delta x very small. Then it becomes a derivative. Same. Basically what I'm saying, it is slope of the secant. Only thing I have to make these 2 points negligible distance apart. Let's do that part also. If I do that one, so in this expression I have to make delta x close to 0. Let's simplify it. If that tends to 0, sorry. Okay, let me do this part. So this will become x square plus 2x delta x plus delta x square minus x square by delta x. These two terms will cancel out. What is left is 2x plus delta x. And since basically divide by this one, and since delta x is extremely small, this will almost be equal to 2x. Okay. So what we get here, we get this for y square dy by dx comes equal to 2x. What is significance of this? What does this term indicate? So basically, let's go back to this point. This mathematical expression, this tells you basically value of y for each value of x. This indicates slope at different value of x. If I want to find out slope of tangent at x is equal to 1, I'll put x is equal to 1. That will give you the slope of tangent drawn at x is equal to 1. If I want to find out the slope at x is equal to 2, I'll put x is equal to 2. So this expression gives you slope of tangent. It gives you formula for slope of tangent. That's why it is in form of a variable. Because slope will keep on changing with x. This indicates as x keeps increasing, the slope is continuously increasing. And you can see from the graph also, if I draw a graph, the tangent here, slope will be less. And here, the tangent slope will be more. So slope is 2x. I'll again come back to the previous case. So give a slope of tangent at all points on the curve y is equal to x square. This is the formula. So depending on how x and y are related, we can find different value of dy by dx. We'll have different graphs, and hence we'll have different value of derivative. And that's the principle behind differentiation. So again, key point what you need to keep in mind here, what is the concept we are used? We can find slope of a secant because it has 2 points. For finding slope, we need 2 points. Whereas a tangent has only 1 point. So how do we find the slope of tangent? Conceptually, we find the slope of a secant, which intersect the curve at 2 points, and we make the distance between 2 points as approaching 0, negligible distance apart. With that, we come to the formula. So in this case, what is the slope at 0.7? So if I have to find slope at x is equal to 0.7, so if we take this point x is equal to 0.7 and draw a tangent, slope will be equal to 2 into 0.7, which is 1.4. And you recall what is 1.4? So if again I go back to previous term, the slope at t is equal to 0.7 will be equal to 1.4 meter per second. That would be the instantaneous velocity at x is equal to, or time t is equal to 0.7 second. If I revert back to previous slide, we'll continue with this later. We'll see some more examples of the same. That's the behind by derivative, right? So that's the slope. So 0.7, if I draw the slope, and the slope, this slope will be equal to 1.4. Right, so I will just have one more general derivation for differentiation, but before I do so, there's another thing which is very commonly used, is called binomial approximation. What is binomial approximation? So this is a term 1 plus x raised to power n, this expression, and this will have multiple number of terms. But this is almost equal to 1 plus nx if x is much less than 1. For a very small value of x, this is the approximation. Okay, if you find it doesn't make sense, let's elaborate further. What does it mean? Let's take, for example, what does it mean? So in place of if I write this expression is more in terms of specific numbers, definite numbers, whereas this in terms of variables. So what you have said, if x is equal to 0.003, n is equal to 5, then this expression, it is actually what you written here, 5th power of 1.03. It is almost equal to 1 plus term n into x. It will be 1 plus 5 into 0.003, which is equal to 1.015. So this way, otherwise finding 5th power of this term is laborious and tedious task. But if x is very small, we can approximate it. And if I calculate using calculator also, sorry, I missed one term. With calculator, it comes equal to 1.01509. So what do you find here? This approximation is actually very close to a real value. And so that's it. So that's what this formula means. So whenever we have this kind of term, 1 plus a small number, and there will be plus sign and minus sign, doesn't matter. If this minus sign, this time will be minus. Any exponent, it can be even a fraction also. It is valid even for fraction also. Otherwise, fraction becomes very difficult to solve. So what you are saying now, if you have to find something like 1 plus 0.003, and they basically have to find some 5 by 2, what will this value be equal to? It will be 1 plus 0.003. Sorry, I will write and into 5 by 2. That's the approximate value of this expression. So we'll use it in the next derivation. That's why I'm discussing it. But this has very wide application. And just to get another example here, let's take something like this. What is 1 plus x cubed? We know the expansion. I'm writing the expansion, the increasing power of x. It will be 1 plus 3x squared plus x cubed. Okay. Now, if x is very small, if x is something like 0.003, you understand what would be 0.003 square? It will be extremely small number. It can be written as 3 divided by 1000 whole square. It will be 9 divided by 10 to the power 6. Extremely. So what we notice here, if the number is very small, is square and higher powers become even more small. They becomes negligible. So when we compare these two numbers, this number and this number, see if x is 0.003, this number will be 0.003 times of this number. So compared to this number becomes negligible. So whenever you have this kind of expression, terms with x square and higher power are negligible compared to first two terms. If x is small, I can ignore. So what we notice, this is what we are talking about here. 1 plus x cubed can be approximated as 1 plus nx. That's the idea behind this binomial expansion, binomial approximation. We'll use it later on. Next slide. Right, let's move on. In the previous case, we have taken y is equal to x square. Let's take a general formula which takes care of any exponent, any power of x. Then becomes a more versatile, more general formula. So basically, what we are trying to find, we are finding derivative. When two quantities are related, y is dependent on x. So rate of change of y or slope of tangent to yx curve at any point is dy by dx. What is that equal to dy by dx? Dy by dx can be, if we substitute the value of y, it can also be written as d by dx of x raised to power n. So either I can say that dy by dx of this expression or d by dx of x to power n, both are same thing, is equal to n into x raised to power n minus 1. What does it mean? So this, if the power is n, whatever is the power becomes the coefficient, and exponent of x decreases by 1. We'll see it number later on also. So this is the formula. Let's see how we arrive at this formula. And let's see, this is and to visualize if this expression, this is a graph which has been plotted. Yx graph, this how this graph is plotted. So some x raised to power n. So again, let's understand the concept here. How do we find dy by dx? Dy by dx is actually delta y by delta x. It is equal to delta y by delta x. Only thing, delta x, when delta x approaches 0, it becomes dy by dx. So it is a slope of secant joining 2 points which are negligible distance apart. So let's apply this concept here. So can we apply this for this case also and calculate? Okay. So what we have done here, again, since we are finding general formula, this is point x here. This is this we have done in the previous sheet also. This is second point, x plus delta x. And how is it delta x? Delta x tending to 0. And then we find the corresponding point y coordinate also. And since y value or y value on y-axis is nth power of x-axis quantity, this point will be equal to x raised to power n, and other quantity will be equal to x plus delta x raised to power n. I mean, these are the points here. So we are finding slope of a secant passing through those 2 points. Only thing, these 2 points are negligible distance apart. Thus the slope of a tangent. Let's do that one. So which 2 points we have chosen? We have chosen points corresponding to x and x plus delta x. These are the 2 points here. So this is what we need to find, this expression. So can we substitute this value? Yeah, let's do that. So this value also, okay, sorry. Let's put those values. This values will be, just substitute it here. X plus delta x 10 to power raised to power n minus x raised to power n divided by delta x. Now let me focus on this part only. Okay, so let me focus on this part. Let me write separately. What is x plus delta x raised to power n? So first what I do, I take x common out. So if I take x common out, when you come out of this becomes x raised to power n, and what is left is 1 plus delta x by x raised to power n. Now for this expression, this is a small term. You notice this is a small number divided by x is a very small number. I can use binomial approximation. What is binomial approximation? Outside the term xn remains same. It becomes equal to 1 plus the exponent, which is n here, into this term. So it becomes 1 into delta x by x. So what is this whole expression is equal to? Whole expression, if I take multiply by x raised to power n, it is x raised to power n plus n delta x. Sorry, let me simply write that one. Not like this, I write in the same line. Okay. So basically, one power will get cancelled. So what is the exponent left? N minus 1. And n into delta x, x raised to power n minus 1. Let's put it back here. So what is this dy by dx expression? So basically we have evaluated this term and we use binomial approximation. So binomial approximation, I have converted the first term. I have divided the whole expression by the first term because I want first term to be 1. Then only you can apply binomial approximation. So what is this term equal to? So let me write the numerator value, x raised to power n plus n delta x, x raised to power n minus 1 minus x raised to power n divided by delta x. So what happens? These two terms gets cancelled and one delta x gets cancelled. This one, what are we left with? N into x raised to power n minus 1. And this becomes the formula for slope. So this is valid for, so this formula is valid for any exponent. It x raised to power 2 by 3, 1 by 3, 1 by 2, 5, 10, basically. So that's a formula, and this formula is very versatile formula, a very, very commonly used formula. Understand how have we arrived at, understand the concept of differentiation, and go through what we had done several times till it is thoroughly understood. This is extremely important concept, and an in-depth understanding will make things much easier. Basically, so we had done it for xy. Sometimes xy doesn't give you understanding what does the slope mean. So again, let's take a physics application. What we are doing physics application, and x-axis we have some physical quantity, and y-axis we have some related physical quantity. Then becomes a typical physics example. So let's do that one also. It's meaningful. And so first of all, when we have this kind of expression, this is meaningful only when y is a function of x, or y can be expressed in form of a mathematical function of x. Then only this kind of dy by dx work. And so whenever you have xy plot, the quantity y-axis, it should be possible to write in terms of function of x. It must be dependent on x. It must be a function of x. Then only. So let's, in this case, physics again. So far we have been using motion of a particle along x-axis. So again, let's use an expression x is equal to tq. So position of particle moving along x-axis is varying with time. So position of particle and time are given here. So time is one variable which we can represent on x-axis, and position on along x-axis is we represent on the y-axis. So we need to find what is the instantaneous velocity at t is equal to 1 second. So let's see that one. How do you proceed that one? So what happened? This was like a mathematical curve. Now we are assigning physical significance. We are replacing x and y with some meaningful physics quantity. What we have done? X has been replaced with t. This is position in meters, and we have taken the graph is equal to x is equal to t. And let's say this is something like 0.25, and this is 0.5 second, this 0.75, this 1 second. So what do you want? We want what is the instantaneous velocity at t is equal to 1 second. Instantaneous velocity would be equal to slope of the tangent drawn here. So what we need, slope of the tangent is given as dy by dx. Okay. So what you need to do, we'll find dy by, so in this case, this is, sorry, not dy by dx, here y is x and t. So this we'll get dx by dt. We are going to get dx by dt. So let's see that how we are going to get. We need here, similar to dy by dx, we put the corresponding quantity of y and x, it becomes dx by dt. Dx by dt will be equal to limit dt tending to 0, x value at t plus delta t. Again, similar, exactly same thing what we have done here. This gives you instantaneous velocity. This is this is displacement during time interval of delta t. This is the time interval. If the time interval approaches 0, it becomes instantaneous velocity. So that's the expression. And if we put those values, so actually again we produce this term, this t here, this t plus delta t. This is corresponding value of x quantity. This will be equal to t cube, and this will be equal to t plus delta t cube. But this is what we have done in previous sheet. But we need not repeat the whole process because we already have this formula. Now we'll not do all those things. We'll just use the formula. So what is formula I'll use? Dx by dt. I'll put the value of x here, d by dt of t cube. So this term and this term are similar. So this is formula is similar to x raised to power n. So here, see, you notice here when we do this one, this x, this term must be written in form of x, same term which is there in the denominator. So here also it is t cube. We are differentiating with reference to time. Then only it is meaningful. So n value is 3. So the exponent becomes the coefficient, and power of t reduces by 1, 3 minus 2. So that's a derivative. 3x is 3t square. So this gives you dx by dt is instantaneous velocity. It gives you general expression for instantaneous velocity. So we know the velocity at all instances of time. What we understand, this equation x is equal to t cube is like a relationship, mathematical equation between position and time. This derivative gives you a relationship between velocity and time. So we can calculate velocity at all instances of time in one shot. So what, without differentiation concept, this would have been a very tedious task. It is made much simple. So if you want to find velocity at 1 second, it will be equal to 3 meters per second. Velocity at 2, I substitute t is equal to 2 here, and that will be 2 square into 3, that will be 12. So velocity at t is equal to 2 seconds will be 12 meters per second. So that's the power of differentiation, and that's what we need to understand. And our understanding will keep improving as we keep applying in different chapters. Application of derivative comes in almost all chapters of physics. So I hope this part is intuitively also you understood. So you have good clarity on it. If not, just go through whichever part is not clear, go through that video part again. See that it is perfectly well understood. So that brings us to the end of first part of differentiation. Next session, I will take up some more example and some more formula for derivative. In this case, we have taken the derivative only for one expression, y is equal to x raised to power n. We'll take up some more for expressions in the next session later. So I'll stop here. Thanks, everyone.